un connotado microbiólogo alemán. Ha sido vicedecano de investigación de la Facultad de Ingeniería Civil en la Universidad de Stuttgart, Alemania. Cuenta con más de 62 artículos científicos publicados en revistas indexadas, ha dirigido innumerables proyectos de investigación y tesis de doctorado, además de haber participado en diversos proyectos con la industria. Su trayectoria académica amplia y su experiencia en temática del tratamiento biológico de aire contaminado son de gran interés para reforzar las líneas de investigación prioritarias aquí en nuestro instituto. La experiencia que Karl tiene en desarrollar soluciones a problemas ambientales en cooperación con las autoridades gubernamentales y la industria alemana son las que nos permiten o visualizamos que podrán aportar nuevas perspectivas de colaboración e interacción entre la academia y los sectores gubernamentales e industriales. Esto también permitiría resolver verdaderos problemas ambientales en materia de aire. La visita del doctor Engesser también será aprovechada para la planeación de un proyecto de investigación en conjunto y el asesoramiento en los experimentos realizados en el grupo del trabajo que está coordinando el doctor Armando González Sánchez. We are very pleasure to have you here in Mexico in the Engineering Institute. Welcome. If you want to start your conference. Sure.
Yeah. Thank you very much, Profesor Noyales, por su introducción e invitación en este instituto famoso en México. Es la primera vez que estoy aquí y estoy muy agradable, y posiblemente porque Armando está trabajando y trabajando, pero mi español no es tan bueno para hablar totalmente en español, entonces ya, pero quisiera cambiar a inglés si es posible. ¿Ya? Porque es más fácil para mí el contexto en inglés. Ya, es mejor eso. This is the microphone I use for here. And this, I don't know. Streaming? Yeah.
Okay, both.
Yeah, it's como en hospital, muchos cables y es muy normal. Entonces we would like to talk about degradation of volatile hydrocarbons. When you would like to have waste air purification, as we are doing, you have to have compounds which are volatile naturally. So we are talking mostly now about these volatile carbons, VOCs, and technical applications in this sanitation strategy. One word only for our institute, the ISMA. We are combining different fields of work. Sorry for the German here. Water, tierra y air. And we are relying on a heavy body of analytics, chemical analytics and biological analytics in order to cover this. I think this is a reasonable structure to work on these problems. To be honest, we are mainly based on water in this institute, and so it's a water-based institute, and so the other areas are covered as well. So we will deal in our lecture with some compounds of interest because they are chemically interesting or interesting because of their use or their problems they present for the microorganisms to degrade them. We are doing environmental business, so we would like to degrade these compounds. So they have different degree of biodegradability and will require different strategies to cope with these compounds. I hope we have time for one big-scale technical application of these waste air cleaning, and if there is time, I will give some outline on saline bacteria. I would not like to stress too much chemistry. Maybe I just hold over some folia in a rather quick fashion, not to do too much chemistry. we were busy with fluorobenzene, for example. You may know chlorobenzene, which is a famous contaminant in water also. Fluorobenzene is a rare compound. It's a very specialty compound, but it presents a very special problem for the bacteria. This is why we selected this compound. Fluorine is a very small atom in comparison to chlorine and bromine or even iodine. So the bacteria have problems to distinguish in size this fluorine from a hydrogen atom. So they are running into problems and sometimes mistake these substituent. You can see this here, the space filling model of fluorobenzene. Chlorobenzene is already much bigger, and as the others are. This is the biggest one, the iodine. So fluorine resembles not really exactly hydrogen. This is hydrogen here, but it is similar in structure. So there are some problems. I will not go into details. This is the bacterium we isolated, Flu 100. This is a lab code for a bacterium when you isolate it. I don't know how familiar you are with microorganisms, so may I give some simple indications what we are doing, and if you know already, then forget it. So it's lab code. We are just isolating bacteria and then describing them later on in more detail, but in the beginning we have a lab code for them to give them a provisional name. There are the bacteria. When you are searching them, you have to go to a place where they are or where they may be. And fluorobenzene is such a rare chemical, and it's so difficult to degrade that you will at no place normally find these bacteria. So we went to a company producing fluoro specialty chemicals, and they had some sort of a biofiltration test system, and we isolated from this test system. We got some wooden pieces which are settled by these bacteria.
Potentially growing bacteria in a phosphate buffer system, incubating with fluorobenzene and waiting. Waiting is a very frequently seen attitude in our lab. You are drinking a coffee and waiting for the bacteria. And when they show up, then you can plate them on a Petri dish. And this is a specialty technique. On this Petri dish, then you can try to isolate individual bacteria. Here you see individual points representing colonies which represent, in this case, maybe 100 million bacteria. In this case, maybe only 10 million bacteria. And in this case, you can try to find the right bacteria which are really growing with fluorobenzene, which means they eat fluorobenzene as their sole nutritional source. And these are very specialized bacteria because you normally will not find them. When you go out to the soil here and isolating bacteria, I'm quite sure, I will nearly bet €100 that you will not find the bacterium growing on fluorobenzene. So it's a specialty. This is a bacterium, not surprising, a normal bacterium. Looks like a cigar, more or less, and here are colonies of these bacteria. What do they eat? They eat, in this case, completely all these halogenated benzenes. This is quite good. They even eat toluene, even benzene, and some phenols, some substituted phenols they will also consume. And they will degrade a very toxic chemical, the dihydroxylated fluorobenzene, which is always inevitably a part of the degradational system in this benzene area. Maybe we will touch this. They can only partially degrade this row of compounds, and they will not degrade these compounds here. This is just a matter of exercise that you can see that many chemicals, or in other words, bacteria can be very specific. They feed on some compounds, but not on similar ones. This is a problem for the engineers. Because normally we would like to grow them on a bunch of compounds which are toxicants in the soil, for example, or in water, and they are preferring only some of this is a problem. They are specialists and feeding only on some of them. This is the sense of this folia. There are some nasty compounds which would never be degradable. Difluorobenzene, it's incredible how we can degrade this, or even trifluoromethylbenzene. It's very complicated. They will grow. We can see this with the so-called optical density. This is a measurement of concentration of particles in a solution. And over time you see an increase with the different compounds you supply for food. And then you see an increase in these particle density, which in the same time means number of bacteria in this case, because we only have bacteria in this system. And you can calculate some growth constant in all this. This is not so important. They grow at different velocities with different compounds. This is quite normal. Different compounds present different velocities, different problems. This is not astonishing. This is just to orientate yourself what you can do with these bacteria and what do they need, what can you supply as a substrate and all this. And you can show that they will degrade fluorobenzene and chlorovenzene simultaneously. So this is an indication that they will grow with the same set of enzymes they use for the degradation. So this is an indication that they will not preferentially use maybe one substrate over the other. They are degrading both at the same time. And this indicates they only have one set of enzymes for both of these chemicals. That's the message. And even toluene and fluorobenzene are degraded at the same time. So there seems to be a common metabolism also for this. When we have a look at the stoichiometry, this is an important value because we would like to know how complete is the metabolism. The problem in metabolism of bacteria frequently is that they will degrade only partially the substrate and will produce metabolites. And metabolites may be more toxic than the original compound. I remember for degradation of trichloroethene anaerobic systems, which may produce vinyl chloride, which is cancerogenic. So you make things worse by biotreatment. You may make things worse than in the beginning. And so you have to know about the metabolites which are coming off. If you have a stoichiometry which is nearly 100%, then you can be sure that they will eat everything. They will not produce any metabolite. That's an important fact for bioremediation stuff or something like that. We will not touch all these different substrates with different biochemistry. This is a nice view when that will only say that these bacteria are producing acid when they degrade on fluorobenzene. This is not astonishing because after degradation of fluorobenzene you will get HF. This is a very strong acid, and so you see in a bronze tumul blue and all these different indicators will give you an indication that acid is produced. And this is very normal. You should only not buffer it too strongly. If you are exerting a too strong buffer, then you will not see too much acidification naturally. And this is what we normally have to do. Now a shocking folia, maybe for some extent. We are wondering how these bacteria may degrade the fluorobenzene. And there are different strategies. You could degrade it when you sit at the table and writing a formula scheme. But we are not bacteria. We are just scientists and thinking on them, on their metabolism. And we don't know what they are really doing at the very end. So we try to find out. So one strategy would be a very good one. Attack in ipso position. I should say first that most of these molecules are attacked by so-called dioxygenases. These are enzymes taking oxygen from the air, both atoms of the dioxygen molecule, and fix it on the molecule to be degraded. So this is the so-called dioxygenation. This initiates, in most cases, bacterial metabolism of benzene, toluene, ethyl benzene, all these different compounds. Not every, but most of them. So doing this, it would be very, could we say, intelligent? Yes, I think we could. This is a human term, intelligent. Bacteria don't know that. So if I would be a bacterium, I say, I would choose the ipso position, because in this case you end up with an halogenated dihydroxy structure, still two double bonds in the system, which is unstable. I forgot the rectangular brackets, sorry for that, which will spontaneously, chemically liberate halogen acid, HF in this case, and you will end up with easily biodegradable pyrocatechol. This would be the most clever strategy. We have solved the problem, the fluorine is out of the molecule, and everything is okay. But the bacteria didn't do that. So this was my idea, and a colleague of mine, he said, it's very clear, it has to be an attack in meta position, because we have a complete pathway for the degradation of 4-fluorocatechol. So he said it should be the attack in meta position. So we were begging for a bottle of champagne. Who will win? At the very end, we did a PhD work on that problem, and we found out that it's the ortho position. So we both lost, and the bottle of champagne was never drunk. That's the way it goes, because this is the most difficult way you can do it, and the bacteria, they're very sporty, so they choose exactly this, exactly the difficult way. So, sporty, not the easy way, but the sporty way. It presents a very difficult molecule. Hal means in this case fluoro, and we have 3-fluorocatechol, which is a nasty compound that creates a lot of problems. And not by these normal pathways we did not find, so we have to define how is this bacterium really doing that. And during this PhD work we were going, this is some time ago, nowadays we would totally sequence it simply, the whole genome, and then we're sitting in front of the sequence and thinking, and we don't know exactly what is this it's saying. I talk to the students, it will be not so far away from the time that you get all your total sequence of DNA on a CD, and you can write it in the evening before sleeping, and you are bored by this sequence, because the sequence, as you know, may not tell you too much. It's a senseless arrangement of nuclear bases, and you have to decipher it. You have to be able to read in this book, and this is difficult. A very promising strategy normally to attack this problem is to use the so-called transposon. Transposons are techniques, is a molecule, a genetic system, which is, you could say, like a virus which can enter a living being, sometimes establishing its nucleic acid in the nucleic acid of the host, and thereby blocking essential functions. And this is what we are doing. We are adding the so-called transposon. The transposon is hopping into the genes at random places. We don't know really where. There's no preference normally. So we have to just afterwards look whether we find a bacterium which have lost the ability to grow with fluorobenzene, because this indicates that the transposon was hopping into genes which are essential for our trait we are analyzing. And this tells you a lot. If you find such a bacterium which cannot grow anymore with fluorobenzene, but can grow with glucose or fumarate or other salts, then you see the basic property of the bacterium is undamaged. It's working, functioning very well. It only lost the ability to degrade fluorobenzene. So the space, the integration, the kind of integration of this transposon has something to do with the degradation of the fluorobenzene. This is what you know in this case. And then you can go for isolating the sequence, sequencing this sequence of choice, and then you can see the genes which are responsible for the degradation. They have to be around this place where this transposon was hopping into. This is theory. In practice, there are many more problems, but sometimes you are lucky.
You are finding exactly this. What is this is such a the map, the genetic map of such a transposon we are using in collaboration with the Institute of Genetics in Stuttgart. I will not go into these details. This is too much. This is simply an organizational map of this piece of DNA, which is hopping around and has the capability of inserting itself into the DNA of the host organism, thereby creating this defect. And we were doing, as it is a chance you only have by isolating, you have to do a lot of work. 6,800 transposon insertion results we were analyzing, and we got a lot. This is a very good efficiency. Normally you will end up sometimes only with one or two or three successful integrations you can measure. In this case it was more, and we can see later on we have another example that these mutants we could analyze, and they produced a metabolite. So different mutations indicated by the different sides of hopping in of this transposon should create different environments, different enzyme defects, and thereby different metabolites therefore produced. Because you are interrupting the sequence of genes which are governing the synthesis of enzymes at different locations. So you should get different results, different metabolites, and this is what we got. So you can find then metabolites which are unknown, nobody characterized this before. Okay, they are not so complicated. This is even me can interpret these spectra, NMR spectra, or something like that, these simple molecules. So even me can discuss with the chemists in this case and feel like a specialist, like a chemical specialist. But we found out that we have this diene-diol structure, thereby proving the difficult way of degradation. And then we were boiling and re-aromatizing this system, all the rules of chemistry. This is not important now, but we could prove the structure, which is very important, which says the integration of these transposon at a certain place in the genome of this bacterium created a metabolite which could not be transformed anymore because the following enzyme is defect, is inactivated by the transposon, and thereby we can find this. Normally the bacterium will not tell you nothing about this metabolism because it has a complete metabolism and it will not show a metabolite. So you have to convince the bacterium very drastically to produce a metabolite. And in this case, it could not grow anymore on this compound, okay? So sometimes we are feeling like a criminalist. We are searching the crime. What are they doing and planning? And they are tricking you sometimes. They are really very tricky bacteria. So they are foolishing a lot. And then we did an NMR spectrum, which is the king discipline in this analysis. I will not go into analysis. We would need a quarter of an hour at least, and I'm not sure whether I got it right. But it is proving the structure of these diene-diol, the fluoro-substituted diene-diol structure, which is the most important metabolite in this case. Yeah. And then we have some measurements of activities, and we see that the fluorocatechol is indeed the metabolite of choice, and it is in nearly 98% of the case. It will go this way, and in very minor pathway will consist of these pathway. So it's nearly absolutely clear. And we have a stoichiometry. When we have 3-fluorocatical degradation, we have fluoride production, which is more or less the same concentration, which indicates we have no other metabolites, no other stuff. We have a clear orientation. And this is the first time that we could show that these fluorocatical can indeed productively be cleaved, and fluorine can be liberated from this molecule. So this has never been shown before. It's important stuff. And by this we could talk about some half an hour. We will not do. This is only the description of the resulting biochemistry we could find. This is the main way. Here we don't know some essential facts. We are not sure about it. It goes further on. At the very end we will end up with these 3-oxo-adipic acid. So this is not very astonishing. These are partially well-known structures, well-known from normal molecules, aromatic degradation stuff. So this is not so important for us. Important is that we have this pathway and we have fluoride liberation of this molecule. We will not go into the phenols because this will create a lot of problems. You see, if the strain feels unlucky, it turns black. Black means that these fluorosubstituted dihydroxylated compounds are polymerizing. You can see this when you, for example, eat an apple or a banana, and oxygen has access to these fruits, then they will turn black or grayish, blackish. And these are similar phenomena. Dihydroxylated compounds present in these fruits attacked by oxygen and they will polymerize. So a very similar phenomenon. And when you come in the lab in the morning and you see your cultures and they are black, and then you can immediately go for drinking a coffee because the day will be another day as you have planned. They are really dead. They will not do any more. Yeah, it's really toxic. So they had a problem in the night, maybe. Maybe not enough oxygen. Maybe they were not in the mood to degrade, and so they are living beings, you know, that this is not not chemistry, pure chemistry. So we will not go for this. We will the result is that we had a productive degradation of these fluorobenzene via 3-fluorocatical, and this was new. Maybe there was an interesting question: how can this pathway be generated? How can we isolate such a bacterium from nature? How did it evolve? From what precursors did it evolve? Because it's a construction. Maybe it was not present before. We were asking in this biofiltration system for this very special trait these bacteria should show. And the hypothesis is just evolutionary theory that we had a pathway taking care of something like chlorinated stuff, with going for the chlorocaticals, fluorocaticals, and these are combined with the degradation phenotype of an isopropyl benzene degradation system, because, and I cannot go into details of this compound here. If somebody is interested, we can discuss this later on. And we have to combine the different traits in order to make a functional pathway. We are doing genetic engineering, but the bacteria are doing this for themselves. So genetic engineering is not only done by mankind, it's also done naturally. A lot of genetic engineering is by natural means generated. So nature is combining a lot of genes every day in a new way, in a new fashion, and we isolated just a certain example of these bacteria and could later on demonstrate this. We will skip this. We had another fluoro-substituted, and go for Butanone, second example, Butanone degradation, a very simple molecule. So simple that you would say, oh, that's boring, so small molecule and cannot be interesting. Butanone, space-filling model of this butanone. It's a ketone derivative, and ketones are not so easy degradable because they are not simply to be oxidized. A ketonic group is resistant against direct oxidation. Here are the data of this butanone. It is used in any liquors, in painting industry, in solvent industry, in a lot of applications. Yeah, you will find it. And you had a lot of tons production per year, so it's worth to have a look at the biodegradation, what is done. Yeah. Okay, we will not go into details of this. Yeah. Some usage of this compound, and this is small biochemistry, not small molecules, small biochemistry, not too long. We can easily see. So normally a butanone will be attacked, and the trick of these bacteria is they will change a ketone structure into an ester structure. You see the difference? There's an additional oxygen. And this ester is easily degradable by a lot of enzymes. Esterases are cheap. You can get them everywhere in every bacterium. But the ketone itself is a difficult molecule. Yeah, you cannot easily degrade it. And then, as I said, it's very easy to degrade this ester to acetate in ethanol. Ethanol goes for acetaldehyde, like in our brain when we are drinking alcohol. And acetaldehyde is the problem, makes headache and all this, maybe for the bacteria as well. So they have an aldehyde dehydrogenase producing acetate, and acetate goes normal TCC. So the trick is the butanone monoxygenase, and you have to show this. Yeah, and yeah, this is for chemists. This is a Crigi intermediate of a biophilic reaction, how to attack a ketone. The chemists are doing the same. The chemists are transforming a ketone to an ester molecule. And this is what the bacteria are doing, but in this case with a very special tricky system, with a flavine-like system, and they're doing this peroxy structure. The chemists are using a peroxy acid. Oh, sorry, this one we need, the peroxyflavine. The chemists are using a peroxy acid structure, combining it with the molecule of choice, the ketone. The microorganisms are using a hydroperoxide flavine complex, doing the same, the nucleophilic attack at this ketone, thereby transforming this ketone into an ester, and then you have one, and then you can degrade it. Yeah. So we like normally to parallelize ketones and esters and chemical action and biological action. We are thinking in many ways chemically sometimes, so this is interesting. Again, this is a boring bacterium, looks always the same. There is no name on this bacteria, you have to find out. Here, more of them, you can see they are agglutinating, gram-staining, gram-negative bacteria. And they are growing in everything the same as before. And here I can show you again, we did the same trick with this transposon mutation again. We like this system. If it works, then it's a very good system, because it tells you about, securely about the function of the genes you are inactivating. This is the big advantage of even nowadays, where you have the total sequencing, mighty power systems now, Illumina sequencing and all this, where you can sequence a genome in 1 day or in 2 days. Yeah? But the problem is, how do you interpret the results? This is the problem. How do you read the sequence and tell the sequence what it means? And if you have a transposon, then the transposon, the place where it was integrating will tell you about the function of these genes at this place. And this is a big difference, and why it helps. And here you see such a bacterium. Here you see such a bacterium. It is not growing on the butanone selective plate, but it will grow on glucose plate. So this bacterium is hit in the degradational phenotype of butanone and will not degrade butanone, but it still can grow with glucose. So it's not hit in essential genes in the central metabolism, but it's hit only in a peripheral enzyme system of butanone degradation. And this is interesting that you can find. Even in this very simple case, I would like to introduce you to a problem where you may be misled by interpreting some metabolites you will find maybe in the medium. When you are incubating a bacterium grown on butanone with butanone, then we found a lot of butanol in the system. So a guy not too experienced in degradation would say, okay, no problem. The bacteria are degrading butanone via butanol and then maybe to butanediol, I don't know. They would search along in this way, in this area, but this is not right. There is an unspecific reduction of butanone in these cells to butanol, but this is normally a dead-end metabolite. It will not be then transformed further. So this is a misleading artifact. So you have to be cautious with this interpretation. In reality, we have these, as I showed, the biophilic reaction, and we get an ester and then total degradation. So be cautious with metabolites when you find them. As I said, they are foolishing you, they are tricky, and they would like to make you believe that it's the hydroxy reduction system which is working in these bacteria. Yeah? Okay. Now we are going for the big plant. I would like to just to show where also butanone is used and some other molecules, a very big system which was in problem. And we are troubleshooters. We are with the engineers, and so they are phoning us up if some problem is shown in a system. I will just show you. And it was a real problem. It was a printing company. They have a lot of printing machines and a lot of exhaust air, which is highly concentrated, and they move this to a thermal power station where they are burning it and transforming it to electricity. This is okay. But then they have storage rooms and high flow streams of low-loaded compounds, low-loaded air, which they cannot burn. This is too expensive. And here you find the application of biological waste air cleaning, because we can purify this air, even it's a high stream volume air, we can purify this and to a reasonable cost. If you would like to burn this, you would have to use such a lot of gas. It's incredible, yeah? You would have to produce hot air. Yeah. And in 60,000 cubic meter per hour, we are thinking in a rather big scale. And so we have to use a biological treatment system. And this is a bioscrubber. Here we have the tubes coming from the company with, I think, about 60,000 cubic meters per hour, going in a distribution system and then in a washing tower. It's a bio-washing system, a washing tower where we try to wash out these compounds of this company into the water and then secondarily purify them in so-called, like sewage treatment plant. It's like a sewage treatment plant. I don't know whether you are familiar with this type of system. Maybe I'm boring you up. So this is the way we are doing it and try to cope with this system. Here's the washing tower. We have support material. In this support material of this size, the bacteria are sitting, and they should not. This was the problem. The bacteria were sitting in this support material, and they are not designed for that. This is a chemical scrubbing unit which only should wash out the compounds into the water system. And afterwards, we would go for these sewage treatment plants, if you like. And here we would degrade these compounds and produce liquid which is free of these compounds, which can then be used again for washing out. And the quality of washing out strictly depends on the residual concentration of the compounds in the water system. If it is bad, the purification procedure, you will have no washing out efficiency and the whole plant will not work anymore, and the neighbors would complain. And if there is some teacher living or a law living in the neighborhood, then you have a big problem. I can promise you. You will not get rid of these anymore. So you should avoid creating the problem. Yeah. Afterwards, it's very difficult. Yeah. Yeah, the data, 400 milligram carbon per cubic meter, 60,000 cubic meter flow. And we have a flow liquid phase, 100 cubic meters per hour. So it's a reasonable big plant. And there was the data of the crude air and the pure air. And normally we will meet our guidelines, which are about 50 milligrams in this case 80 milligrams per cubic meter is the limit we can exhaust. Sometimes if we have a high load, then we will see the peak also in the crude air, in the pure air. But then the plant run into problem. We get a lot of biomass. This is the view to the grid of the support material from below. And you see now the whole plant begins to plug. So the bacteria don't know that they should not grow here on this support material. So they are just settling down, growing and growing and growing. And at the very end, it gets really nasty. Yeah, you have tons of pudding. We say pudding, pudding, yeah. That's worthless biomass. We cannot make use of that. And they are plugging the system, and the blower cannot blow air through the system. It will go down, electricity demand goes up, and so they will shut down the plant, and it's over. Solution is, 4 people, 5 people with gas masks, they have to go in, ship out all this stuff the whole weekend, because production has to go on. And after the weekend, cleaning all this stuff and bringing it back to the system again. They did it twice, and then they were fed up. They didn't like it anymore, and they were calling us and say, hey, you should do something. We don't know why this happens. And so it's even worse, getting worse, and so it's over, no function anymore. Yeah. Too much biomass. This is in the beginning. If it works, these are the support material of this size, about this size, diameter, so rather big, should not plug, should be okay. And afterwards it's growing more and more and it's full of biomass. So this is a catastrophe, yeah, so it will not work anymore. Yeah, we solved it. It was a problem of, a very simple problem. The aeration in the sewage treatment part was defect. So they could not degrade it anymore. So all the bacteria moved to the air part where the washing out system is, because there was air, air to breathe. And so they went there and settled down at this place. And they did a second mistake. There was a guy who was taking care of this plant, very good. And normally this is not the case, and this is one of the problems. And at Friday, when he was going for a weekend, as he would like to drink a beer, he thought, these guys also would like to have a beer. So he spent them 200 liter of ethanol or 300 liter of ethanol Friday evening and said, have a nice weekend, guys. And this is wrong, because many of the compounds, they did not degrade. And so they were feeding primarily on the ethanol, because ethanol tastes good. And they forgot all the complicated ether compounds, butoxyethanol, methyl, and all this stuff. And at Sunday, they begin to think, there are some stuff left, maybe we should degrade this also. But there's no time. Monday morning, new stuff comes, so we will wait. So they did not degrade the compounds, and we said, no alcohol at Friday evening. Yeah. You may drink your beer, no problem, but not the bacteria. Yeah, so they should work at Saturday, Sunday, they should work on the rest of these compounds. And these two solutions were enough to solve the problem. They repaired all this oxygen system and it worked again. So we could save it. You are still fit enough for another problem of benzyl alcohol? This is what we consumed in our lab. These are 2.5 liter bottles or 5 liter bottles. This means we are using a lot of substrate to create waste air, which is presented from our customers. We would like to imitate the system in our lab, and you need a lot of substrate. Sometimes it's a big problem to create an artificial waste air situation in the lab at a reasonable scale. You cannot work, microbiologists are working with columns of 5 centimeter diameter, 20 centimeter height. This is a joke. You cannot work with such a system. So we are using 200 liter fermenters, but this is in technical terms a very tiny, small plant. And the scale-up factories are rather big. We should use a bigger one, but you cannot pay for all these trials. So even then you use a lot of substrate and it costs a lot of money. Yeah, this is a company producing, it's a difficult stuff. They are using wolfram compounds, sintering process. I cannot even describe it in English correctly. They are doing hard metals, preparing hard metals from very soft mixtures of metal and all this stuff. And they are using benzyl alcohol to keep this in a mixture before burning it, before sintering it. And during this process, benzyl alcohol evaporates from the system and you have your problem air. And you have to purify. Now, this is our business now, how to purify benzyl alcohol air. And we did some research on that. I will not go into details. The main problem is benzyl alcohol was oxidized, but we used a wooden piece system, a carrier material. The problem was that benzoate accumulated. So there was only a partial metabolism. They did not totally degrade it. They activated the benzyl alcohol, oxidized it to the benzaldehyde, and this was the problem of smell. People were complaining in the neighborhood because it smells like almendras grill. And now maybe it's an interesting smell, but only some minutes. Then you don't like it anymore. We were busy also with a company roasting coffee, and and I thought, oh, this smells good. Why do that? That's no problem. Oh, yes, it is. When you are smelling 24 hours a day coffee, you don't like it anymore. You like it in the morning or during day over, having a small coffee, then 5 minutes, and it's okay. So that's the difference between professional use of others and private use. Yeah. So the benzoate accumulated in the filter system, and benzoate is very acidic. It makes the system acidic. You get a pH of 3.5 or 4, and this kills most of the bacteria with the exception of these acidifiers, I would like to call them. So very individualistic and egoistic bacteria, which are only interested in acidifying the system, killing all the others, which would like to make a fair, good degradation of benzyl alcohol and benzoate. They are killed. And they are living on this small portion of energy they get from benzyl alcohol to benzoate. And this is the actual planning problem. We are in the process of solving this problem at the moment. It's very difficult to hinder these acidifiers to kill all the others. So you have to take care of the rest of the bacteria which would like to do a good job, but they are hindered by these bacteria. That's my interpretation. So we are rushing through because what I would like to show you is, this is the problem. We get a very good degradation or it's not degradation, it's partial degradation, it's transformation. So the bacteria are transforming benzyl alcohol to benzoate, and this will even crystallize. What you see here are needles of crystals of benzoic acid. Incredible. When I came to this place, they said, they had a very complicated isolation procedure, mass spectra, NMR, and all this, the full machinery. And I said, I would suggest it's benzoate. Oh yes, how do you know that? And I said, that's very clear. I would assume that you have accumulation of benzoate here and crystallization. Okay, it is new. We didn't find such a lot of benzoic acid in the filter system. We are calculating that now in running filter system we have about 6 to 7 tons of benzoic acid accumulated in the filter system. Tons. And you have to get rid of this problem. So you know in lab it's only a very small problem. In reality it's tons of benzoic acid. And what to do with this system? How to recreate it, we don't know at the moment. I think maybe we have to change and burn it. Burn the material totally, yes, and then restart new. Because if we would recreate the system, I think we will end up with a totally destroyed wooden material, and it's not a good support material anymore, and I think it's hopeless. But I will not confront the people up to now with these realities. So we are just waiting until they find out, and then I will tell them. Otherwise they will kill you. It's a very dangerous job to be advisor. You are killed sometimes, or in the danger, when you tell them what they did. So we are just skipping that. This is the plant. Now in the old status, now we have a bigger one, 6 boxes of this type, the washing system. But as I said, I will not go into more detail. The problem is, at the moment, it's not solved. We are running into this acidification problem, and we have to be carefully looking for a system avoiding these. And this is our problem and our aim at the moment, our research, that we can establish a running procedure which copes with this situation. So now we are going on. This is at the very end a working biofilm. Yeah, slime, you would say. A nasty slime, but it is our job to create this because these are numerous bacteria and they are doing the job. They are degrading the compounds. We had a famous example in automotive industry in Germany, and they had a bioscrubber system also. And they phoned me up and said, our bioscrubber will not work anymore. And I said, what did you do? You had, maybe you did something strange. No, we did nothing. It's all normal. And that cannot be. You did something. Our guy was cleaning the apparatus with a high pressure steam apparatus. And now it's clean again, not so dirty as it has been before, but no function anymore. And I said, yeah, that's clear, because you eliminated the function. By cleaning, you did the wrong stuff. Yeah, it's not dirt and slime, it's bioorganisms. So they learned. It was really interesting. Yeah, that's me. That's a joke, just to wake you up again. I was going to Mallorca, isolating some bacteria from the saline, salines, together with my friend Ramon Roselio, and we were isolating benzoate degrading bacteria from saline system, because you will find them only in salines. Why did we do that? Maybe we have time, I will explain you, well, otherwise I will skip it. So I was collecting from the saline system. Here you see the salt heaps, concentrated saline liquor, you could even say. This will contain already something about 10-15% salt concentration now, so medium concentration. And then we are measuring the salt concentration with a refractometer, and then we know where we should get our specimen. Not to get too much salty water, because these are different bacteria. And here it is. Yeah. I didn't know at this time, but it is. We found the bacteria. And now it comes to the problem, why do we search for that? This was not just for a joke, to have a nice trip to Mallorca, but it makes sense also scientifically. We had a company which was producing aromatic peroxides. Aromatic peroxides, benzoyl peroxide, for example. And the way they are doing that, they are producing it from benzyl chloride, hydrogen peroxide. They're producing benzoyl peroxide, and HCl, you see. A lot of chloride, salt. This is salt. So that's the justification that we are going for the salines, because we are searching bacteria which can degrade benzoate in saline conditions, which is normally not possible. Salt is conservating, is preserving, you are killing fungi and bacteria by adding salt. So you need special bacteria which survive salt and degrade benzoate. And this bacteria we were searching for. When you are doing stuff with your car, for example, repairing your car, getting away the rust, you are using peroxide starting compounds to make a sanitation of this material. And a lot of other stuff is used with this peroxide stuff. And we were going for this salt concentration and checking the sodium benzoate concentration. They had this problem. And when they contracted us, they said, okay, you would like to make holiday in Mallorca. No, I said, not holiday. Why do you not use bacteria from our sewage treatment plant? And I said, maybe because these bacteria are not there. Otherwise, you would have encountered them already. So they said, no, we will try. Okay, then try and come back if you did not have success. And they didn't have success, naturally, because in Germany we have not, these bacteria are normally not. They will stop growth at about 5% salt. They cannot grow anymore, 5-6% or more, something like that. So they came back and they said, okay, we pay for that, partially at least you can go for Mallorca and get these bacteria. And then we found them out. Here are the bacteria in Nomaske contrast, growing at 20 millimolar benzoate at 12% salt, very reasonable salt concentration without goodies, without what other people are doing, goodies, which is some amino acid mixture, some sugars, some other stuff, which the bacteria like a lot and helps them to survive. This is a harsh condition. They have only salt, only benzoic acid. This is strong, strong. And these are the bacteria again, just to show them different names, different Halomonas strains which we are identifying. And I will not go into detail, we have not the time, I know, that's too much stuff. We solved the problem at the very end. We developed a procedure degrading benzoate under these conditions of 12% salt. We would like to spare them a lot of money, but unfortunately we helped them also in developing a chemical procedure, acidifying, precipitation, and then afterwards biological application. This would be the optimum and would spare them 150,000 euro per year at least cost. And so they realized at the very end, the chemical procedure because it was some 10,000 euros more expensive only, and you know, chemists are chemists, and so they are relying on a chemical method and not on a microbiological one. It's too complicated. So I will just skip all this and go to the last problem. Maybe it's interesting for you in this area here. Deep Horizon accident 2010. We had this explosion in the Gulf, and it was not a Mexican company. I think it was BP, British Petroleum. Was incredible what they did. Yeah, at the very end, all these drilling facility exploded, and all the people were killed, and they sent 780 million tons of crude oil into the Gulf, and this makes a nasty impression for press, for the people and reporters and all this. And in order to avoid all this, they used Corexit. Corexit is a lubricating, dissolving mixture, a dispersant, which they were distributing by aircraft. You cannot see in this picture here the crude oil. It's some reddish coloration of the seawater. Just to disperse the crude oil, to resolve it into small droplets which are partially sinking down, and you increase the surface volume ratio. So you increase the degradation velocity to some extent. The problem is Corexit. This is not ambrosia. This is not glucose. Yeah, it kills a lot of organisms also. So this is not just funny. It's an emergency action, or we are not even sure whether this really helps environment or not, but they did. And most of these consists of butoxyethanol. This is the last example, I hope. Butoxyethanol, which is an amphipolar compound solubilizing this oil to some extent, like a soap. Yeah? It has a function of a soap. It's degraded, so we had a PhD work on that, and again, I was interested in this simple molecule and said, no, nobody had a look at butoxyethanol. Maybe it's simple, but maybe it's somewhat more complicated and we can learn a lot. And so we had a PhD work, Christine Wojski, you know her. And she was doing a good job, needed some time. Yeah. But now we know that it's butoxyethanol, which is produced, then acetic acid, butoxyacetic acid, and then it is cleaved. The difficulty is to cleave this ether bond. This is a very stable bond. You can hardly cleave. Even chemists have difficulties in cleaving that. And bacteria are doing this. She isolated a lot of different bacteria which can degrade this compound. We were writing to BP and asking whether they need help in biodegradation of this stuff. They did not even answer. So they were not interested in that. So we did again these transposon mutations we are now familiar with. And the interesting stuff I would like to present you here is where does this crucial enzyme comes from, which is cleaving the ether bond here, because these actions are not so complicated. This is normal, more or less normal alcohol dehydrogenase, aldehyde dehydrogenase, not so complicated. But the cleavage of butoxyacetic acid, this is difficult. And where does this enzyme come from? And she found out that there is in eukaryotes, like you and me, there is an enzyme busy in membrane lipid synthesis. And this ceramide, very long chain fatty acid hydroxylase, from yeast for example, is an enzyme which can, using oxygen, can hydroxylate specifically in neighborhood to this group here. They can make a hydroxyl group. And that's all the enzyme is doing. Using this substrate, very long chain fatty acid. Yeah. And it seems as if the bacteria engaged this enzyme. They found it in the grocery store, in the genetic store in nature. You know, a lot of genes are around in nature. Bacteria are dying, yeasts are dying, they send their DNA in the environment, it's degraded partially. So there is an interchange of genes in the horizontal gene transfer. And so maybe the bacteria picked these genes up and were establishing them in their own system, and now using it for a very different task, a very short chain stuff, and hydroxylating it here in these stuff, yeah, similar to that what we had before, you know, in neighborhood alpha hydroxylation, and this creates an unstable adduct, and we get disintegration to butanol and glyoxylic acid, easily degradable compounds. So maybe this is the explanation. So we did up with the sequence of the genes. She did a 3D structure of these enzyme, and then comparing it to the sphingolipid biosynthesis enzyme SCS7 in red, and in green we have our enzyme. And you must admit it's so convincing that we would like to believe that this theory is right, that we are just using another type of task enzyme and employing it for our task of degradation. Because nature already invented this enzyme, and nature, as human beings, are lazy. They would not like to do really new stuff. If there is something already okay, why not use it? And so they make use of a pre-existing stuff which is in nature already. This is all. I have to thank all the people working in this long research. I cannot even mention all of them. We had just some of them very special. Christine, I was talking now about Longeren. And naturally, Armando, who invited me, and he was in Stuttgart, and we were discussing a lot about H2S and chlorinated triglyceride stuff and all this, just to interchange. And so I'm glad to be here, and if you have questions, please ask. Yeah. Yeah. By the way, I will be present here some days more, so if somebody has the feeling he or she would like to discuss more details, then Armando is our contact person. He will organize that.
Muchachos, ¿tenemos alguna pregunta para Karl? Ahí, por acá.
Solamente quiero saber cómo se están manejando muchos compuestos muy tóxicos. ¿Cuáles son las medidas de seguridad que se llevan a cabo cuando se llevan a cabo los experimentos en su laboratorio?
It's mainly, I may answer in English. It's mainly a problem of explosivity and of working with glass, but not really toxicity. We have exhaust cabins and all this, and we are taking care. And we had no real accident. Sometimes people get problems when they're working with bacteria and they broke a glass and they get some drops in the eyes, for example, if you don't take a gafas de protección. And then you have to go to the eye doctor immediately to clarify and get some antibiotic and all this stuff. But so we had some small accidents, but not bigger ones. It's more dangerous when you are working with knallgas, with hydrogen-oxygen mixtures, which we already also did. And this is a real explosive problem. There you may have real boom, and the lab is gone. The chemists have more problem. So in our case, it's toxicologically not so problematic, at least I feel. We are working very carefully and wearing gloves and all this stuff and protecting ourselves from... You are right, because it's gaseous compounds and it's more dangerous than compounds solubilized in water. So theoretically we have bigger problems than the wastewater people. Yeah? But H2S is also very toxic. Yeah. Yeah.
¿Alguna otra pregunta que quieran hacerle? Por ahí al fondo.
Thank you for your presentation. It is possible to find or use this kind of process to specific break the aromatic rate of bigger molecules?
Yeah, okay, in this case they are not volatile anymore. So naphthalene is the limit more or less. But yes, you can go up to degradation of pyrene, which is a 4-member aromatic. But the higher stuff, benzpyrene and all this stuff, it's attacked in a non-systematic way. It's by fungi, for example, also. So it's not a clean biochemistry, I would call it. It's oxidation, like lignin, but you get a mixture of compounds. It's nasty biochemistry. We don't like.
And a second one, sorry. What is the waste management of the cleaning products of the big scale plant?
Yeah. Okay, our measure of quality is the concentration of the compounds as in a sum measured by FID, flame ionization device. This is our measurement, and people have to pay for that if they will not meet these requirements. So you have a law, purification law, which states that you have to go down to 50 milligrams per cubic meter carbon, or 80, depending on the authority. And if you meet this requirement, you are okay. Nobody is interested in the kind of air or doing more research on that. It may be a problem if you have a cancerogenic compound in the air, like automotive industry, when they are having benzene in the air. This is a special problem. Then you go down to 5 milligrams and less, and this is hardly to be accomplished by these machines. Maybe you have to burn it or adsorb it on activated charcoal.
¿Alguna otra pregunta? Por acá otra vez.
Las aguas residuales que se generan de la industria petrolera, en particular de la refinería del petróleo, generan una gran diversidad de contaminantes que son demasiado tóxicos. Para el tratamiento, ahorita con lo que usted presenta, se genera, son tóxicos en la mayoría de los casos, pero cuando se empiezan a degradar, ya sea con una fuente primaria o secundaria de carbono, se generan otras componentes que son aún más tóxicos.
Sí.
Ustedes, durante sus experimentos o como la experiencia que puedan tener, ¿cómo se debería de tratar ese tipo de aguas? ¿Es un parámetro de control? ¿Sería la toxicidad medirla a través del camino metabólico que se lleva a cabo para la descomposición mineral de estos compuestos? ¿Cómo hacen su tratamiento para ese tipo? Aquí en México tenemos un verdadero problema porque la mayoría de las aguas residuales son difíciles de tratar, entonces se utilizan métodos combinados, pero aún así se tiene mucho problema con la elevación de la toxicidad en cada una de las etapas del proceso para cumplir con una cierta normatividad. ¿Cómo ustedes están, o cómo se abordaría el problema, cómo lo están abordando ustedes?
It's a very good question and a difficult question. If I understood it right, I was talking about metabolites, and exactly because of this, that I would like to know during a degradation what happens. And the engineers normally are not interested in that. They have a look at the procedure. Do you degrade it? Yes. Okay. They are not interested in any metabolite or outcome, reducing the concentration in air. Primary goal, fulfilled. And this is not true. In medicine, you naturally have to show, when you take a medicine, the people have to show what are the metabolites in body. What is the body doing with these compound? Very clear. Nobody has a doubt about that. But in environmental chemistry, nobody is really interested in. And this depends on the complexity of the air, what may happen in environment, what is generated. We are doing a lot of degradation studies, which are metabolite studies at the very end. And engineers are asking sometimes, why are you interested in such complicated stuff? Do we need that for purification? Not really. Maybe not really needed. In the case of the benzoic acid I was showing, yeah, it hinders the process. But this is a rare example. Normally in your question, the toxic problems are not touched and not addressed. And naturally, burning it, the best solution is burning. But you cannot pay that. It depends on the concentration. If you have an autothermic system where you can burn it, I would burn it. I would never recommend biological waste air cleaning. Would be responseless. But if it's a concentration of 400 milligram per cubic meter, there is no method, and you have high volume stream, 50,000 cubic meters per hour or more, there is no method which can compete with this problem. It's all too expensive. Yeah. You cannot do adsorption, much too expensive. Activated charcoal is much too expensive. You cannot burn it. What will you do? And so, biological system, if it works in these limits I was addressing, it's without competition. We have no other choice.
Karl, thank you very much for your talk. I'm going to ask Armando if you give a gift to Karl and a diploma. I have the gifts here. Thank you again.